Hello, everyone. Welcome to today's live broadcast, Analysis of Chemical Contaminants in Drinking Water, 2 techniques to analyze pesticides and disinfection products in drinking water in less time. Today's webcast is presented by LabRoots.com, the leading social media site for science professionals, and sponsored by Thermo Fisher Scientific, a world leader in servicing science, whose mission is to enable customers to make the world healthier, cleaner, and safer. Thermo Fisher Scientific helps their customers accelerate life sciences research, solve complex analytical challenges, improve patient diagnostics, and increase laboratory productivity. For more information, please visit www.thermoscientific.com. We have a few announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit your questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to get to as many of your questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please let us know by clicking on the support button at the top right of your presentation window, or submit your problem through the green Q&A button lower left. We'll try to resolve any issues. I would now like to introduce today's speaker, Dr. Jonathan Beck. Jonathan Beck is a Senior Marketing Specialist for Environmental and Food Safety with a focus on ICMS MS. Jonathan received his BS in Chemistry from the University of Minnesota and received his PhD in Chemistry from the University of Missouri, Columbia. He has spent the last 10 years at Thermo Fisher Scientific, with 8 years focusing exclusively on environmental and food safety solutions using the LCMS triple quadrupole instruments and high-resolution LCMS instruments, as well as ICMS MS. I will now turn it over to Jonathan for his presentation.
Thank you, Brenda. Today I'm going to talk about 2 different applications in the webinar today. The first one will be the analysis of haloacetic acids in drinking water, and that will be using ion chromatography MS. That follows EPA Method number 557. The second half of the presentation today will focus on the analysis of pesticides in drinking water using an online solid phase extraction and pre-concentration technique, and that follows EPA Method 543. After that, I'll give a quick conclusion on the webinar today, and then we'll open it up for questions that you might have at the end of the presentation. So let's start with EPA Method 557, which focuses on the analysis of haloacetic acids in drinking water. So how are these disinfection byproducts occurring in our drinking water? Basically, it's a process that can occur when water is treated at a water treatment plant, specifically by ozonation, chlorination, which can include either chlorine or chloramine. And there's a reaction that occurs in this process that creates these haloacetic acids. Basically, they can vary in concentration due to the amount of organic material in the water. So these levels can change depending on the season of the year or how much organic material is present in the untreated water. They are a compound of concern because they do have health impacts. They're known carcinogens. Chloride, for example, can affect the nervous system. It can also affect fetal development and cause anemia. Bromate, as you can see, is a known carcinogen. Chlorate produces various other health issues, including acute renal failure, and chronic exposure over a long time to these chemicals could increase your risk of cancer. So they are regulated under the Safe Drinking Water Act of the United States, and the EPA has promulgated to the states to perform this analysis for public drinking water supply. So that just goes to show who should be interested in haloacetic acids. Well, we all should be interested in them because we all drink water. So anyone who drinks water that is treated, it's of our vital interest to know that we're not having too many of these haloacetic acids in our water samples. So what's the occurrence of these different byproducts? So haloacetic acids, as I mentioned, are formed when chlorine or bromine or other disinfectants react with naturally occurring organic and inorganic matter in the water. This slide just kind of shows the breakdown of the products that are created. The haloacetic acids are roughly 13% of the total disinfection products that are created, and then you have trihalomethane accounting for about 20% of the disinfection byproducts. The interesting thing you see is there's still about 2/3 of these products that are unknown halogenated organics. Iodine can be present. Some studies have shown the presence of iodated haloacetic acids. So as we investigate further and learn more about these disinfection byproducts, this list may certainly expand to cover more disinfection byproducts to help cover up that 62% of the unknowns that we see there. So the list of haloacetic acids that are analyzed and identified currently can be broken down into two lists. There's a list of 9 different haloacetic acids that you see here. Everything from monochloroacetic acid at the top, so that has 1 chlorine attached to the acetic acid, down to trichloroacetic acid, which would have 3. And then we have the bromine family, mono, di, and tribromoacetic acid. And then we have combinations where you have a bromine and a chlorine, or a combination of the two in there. Commonly in the U.S., the EPA is regulating the top 5 that you see above the middle dark line. But there are inclusions of the additional 4 that can be analyzed as well. So depending on the regulatory agency, for example, if it's outside the United States, they may require more than the 5 that are shown on this slide. But for most analysts in the United States, the focus are the top 5 that you see here. However, this method does include the analysis of all 9 of them, and we'll show the results for all of those. So just a background on the regulation in the United States, total trihalomethanes were first regulated in the 70s, and then the disinfection byproducts came in the late 90s. The HAA 5, which are the top 5 that we talked about on the previous slide, were added with the addition of bromate. So this is required to monitor all 5 of those at all plants that disinfect with chlorine. And they're required to report the total of the 5 that you see here. And the total level, maximum contamination level, should be less than 0.06 milligrams per liter on an annual average basis. There's some additional regulations that came out in around 2006. Again, the same level to have that less than 0.06 milligrams per liter, but they did specify some specific levels for monochloroacetic acid and trichloroacetic acid that you see listed here. And they also noted that the dichloroacetic acid should not be present in any of the samples. So a summary of some of the EPA methods that have been promulgated for haloacetic acids, as well as bromate and Dalapon. In this, you can see method 552.2 and 552.3 available. Those use liquid-liquid extraction and derivatization prior to analysis on a gas chromatograph electron capture detector. So that's a commonly used method for most laboratories now for the analysis of haloacetic acids. But recently, about 3 years ago, the EPA released method 557, which deals with the ICMS-MS detection of the haloacetic acid. And I'll talk about the differences between the two methods and the advantage that 557 has over 552. There's also the ability to do 2-dimensional ion chromatography with a direct injection, and that is currently pending. I will not focus on that analysis today in today's presentation, but it is something that the EPA is considering as well for the analysis of the haloacetic acids. So US EPA method 557 uses suppressed ion chromatography with mass spec or MS-MS triple quadrupole detection, and that's the method we're going to focus on today, the triple quadrupole. It's a direct injection of 100 microliters of drinking water, and you divert the matrix that could be present in the drinking water to waste so that it does not go into the mass spectrometer. The nice advantage of method 557 over 552 method is that it eliminates the liquid-liquid extraction steps, as well as the derivatization that is required to take place before analysis. So anybody who's done liquid-liquid extraction knows that it uses a lot of solvent, so you do have solvent waste issues to deal with, and then the derivatization step can be not as reproducible if your technique is not very good with that. So it's just another step that you can eliminate by going to the 557 method to get rid of that. We don't have to worry as much about co-elution of our analytes of the haloacetic acids because the MSMS is a selective detector. And I'll talk about that when I show some chromatograms later. But basically, you don't have to worry about co-eluting peaks as long as they have different masses. MSMS also provides molecular information, giving us more confirmation that would be available with techniques such as HPLC or GC-ETD. It's fully automated. All you need to do is load up your samples in the auto sampler and let the instrument take care of the analysis. And the recoveries that were achieved during the analysis, during the test, were greater than 90%. So ion chromatography, for anyone who is not familiar with ion chromatography, I've just put a slide up here showing the different ion chromatography systems that we currently offer at Thermo Scientific. From left to right, they increase in complexity and ability to do more involved experimentation and give you more options. The instrument that I am going to focus on today, the instrument that was used for this analysis, is the one on the far right, the Thermo Scientific Dionex ICS 5000 Plus IC system. And that's the one that's used for the EPA 557 analysis. We do have a couple of others that are in that family. The three on the right are all capable of reagent-free ion chromatography. That is a really nice feature. What that means is you don't have to prepare any of your eluents beforehand. You simply use deionized or distilled water and add that to the system, and the system creates the eluent for you automatically. The ones on the left, the three instruments on the left, you do need to create the eluent and put it in the solvent bottle at the top. The two instruments on the right are also capable of higher pressures. Ion chromatography systems are made to be metal-free in their past, so there are pressure limitations. The two instruments on the right can go to higher pressures than the ones on the left. The higher pressure going up to 5,000 psi, and the others were limited to a lower psi, about 3,000 psi. So how does ion chromatography work? Well, on this slide, we're going to take a close-up look at the small stationary phase particle that's contained within the ion chromatography column. So ion-exchange chromatography is generally divided into two different modes, anion exchange and cation exchange. This diagram here is going to show how the system works under anion exchange mode, which is what we use for the haloacetic acid analysis. So basically, the orange dots represent the analyte anions that are different sizes in here, and the red and the blue ones represent the eluent ions. Those come in the mobile phase. So at the beginning of the IC experiment, the anions bind to the ion exchange active sites, which are contained on the stationary phase of the particles. As the eluent flows through the column, these analytes are coated on there, and then we're going to have our sample come in, and that's what we have grabbing onto the active sites here. As we increase the amount of mobile phase concentration, in this case anion elution, we're using hydroxide, we're going to strip off our analytes and replace them with the OH. So as we increase that strength, the affinity of the molecule determines when those will elute, and we're able to separate our ions of interest based on that strength of the eluent coming through the system. Of course, coming through to the mass spectrometer, we're going to have some anions and cations that are not compatible with the system, and I'll talk about how we clean that up and make it compatible with the mass spec in a couple of slides here. So what are some of the advantages of using the IC versus GC or say HPLC? For this method, 557 for haloacetic acids, as I mentioned earlier, there's no derivatization that is required. We get very good selectivity with the ion exchange column. We get very good sensitivity because we have a very low chemical noise background. IC is ideal for the separation of very small and polar compounds in addition to haloacetic acids, and I'll mention some of those later. And my favorite part is that you don't have to use any solvents with this. Again, you just add water to the system, and the Anion generator creates the mobile phase. by mixing water with, in this case, potassium hydroxide. So how is that created? This slide is going to show how we generate that eluent in the system. Going from left to right here, we've got our our IC pump on the left in the blue square, and that's delivering water. That flows down to our eluent generator, which is basically a large plastic bottle inverted, and on the bottom of that bottle where the cap is, we've got a platinum cathode. And doing a little electrochemistry, we can generate the right strength potassium hydroxide to go through our ion chromatography column. And by varying that current on the platinum cathodes and anodes, we can change the concentration in real time. So as we generate the KOH, potassium hydroxide, it flows through an anion trap, and then we degas any hydrogen that might be produced, that is produced during this process. And that's removed from the mobile phase so that we don't have any bubbles, and we just have potassium hydroxide going through our system. So those of you that might be familiar or using IC and using it as a standalone system, you're probably familiar with a conductivity detector, and that's how we measure what is coming off of the ion chromatography system. So there's a couple of different ways of doing that analysis, and we're going to focus on what's called suppressed conductivity. So suppressed conductivity removes the high background of the potassium ions from our system in this example, so that we have a low background of just water coming through, and then we measure our analytes against that background. So that's the bottom blue cartoon chromatogram that you see here. We measure our anions in this example against a low background. The other way of doing it is to not use suppression, and then you get a dip in your chromatogram when the anions elute, and then the software would invert that and look like a chromatogram that we're all familiar with the peaks going up. The advantage of the suppressor is that we get that nice clean background. And the other important thing and take-home message here is that the suppressor makes the system compatible with a mass spectrometer, because potassium is not a volatile salt, so if that goes into our mass spectrometer, we will quickly dirty up the instrument and make it unusable as we precipitate all the salt, the potassium salts, out of the system. So the suppressor is what allows us to couple the ion chromatography system with the mass spectrometer. So the ICS 5000 Plus system is the one that is used for the haloacetic acid analysis. It has 2 pumps in it, so we've got a dual system that can have 2 different channels. We have the suppressor in there as well. There's also an important feature that is a temperature control for the haloacetic acids. Some of the haloacetic acids are sensitive to temperature, and the method from the EPA dictates that we need to use 15 degrees C on the column. So the bottom section of the instrument on the left, right, let me draw a little arrow here so you can see what I'm pointing at. This section here is the column oven, and it can heat or cool the system and allow us to keep that column at 15 degrees. The top of the system, right here on the upper left, is the auto sampler. So this is where you're going to load all your sample vials, and that takes care of the injection of 100 microliters in this example. You can, of course, have different injection volumes if you need to for different analysis. The top box on the right-hand side is where the 2 IC pumps are housed, and then the bottom right section here is where our eluent generator cartridges are contained. So this is the IC system. It is a benchtop system. It sits on the benchtop next to the mass spectrometer, and you can fit that on a benchtop that's, let's say, roughly 4.5 feet across, including the mass spectrometer, and then it's about 2 to 3 feet tall from top to bottom. So the nice thing about the 5000 system is that we do have the capability to run at the higher pressure. So this one will go up to 5000 psi, and that allows us to use smaller particles when available to get better separation and more narrow peaks. With the 2 eluent generators housed in the bottom right, you can dedicate one to the anion detection and one for cation separations. So without having to change tubing and eluent generator cartridges, you can handle all of that on one system. Okay, so let's take a look at the IC conditions that we ran for this experiment. You can see it's actually a gradient, so those of you that have done GC or HPLC, it's the same idea, except instead of using heat in the case of a GC or increasing our organic percentage in HPLC, we're going to change the strength of the potassium hydroxide gradient here. So we start out at a concentration of 7 millimolar potassium hydroxide. We then ramp that up to 18 and then 60 millimolar, hold that there, and then bring it back to initial conditions. The whole runtime for all 9 haloacetic acids takes just about an hour. If you're only analyzing those 5 haloacetic acids, you can actually shorten the method a little bit and have them all eluted in about 45 minutes. The columns that were used for this experiment are the Dionex IonPack EG24 guard column and the IonPack AS24 IC column. You can see the column dimensions there. Suppressor that we use is a AERS 500, 2 millimeter size, and the column temperature held at 15 degrees C. The flow rate of the potassium hydroxide gradient was 0.3 milliliters per minute. So that flow rate, if you're familiar with LCMS, is quite compatible with electrospray systems that we use. So talking about the mass spectrometers that we are going to couple the IC with, we have 2 options that I'd like to highlight right here. We have the TSQ Endura and the TSQ Quantiva. The TSQ Endura is our mid-range system, and the TSQ Quantiva is our highest performing triple quadrupole instrument. For this analysis, I used the TSQ Endura, and it works quite well and gives you the sensitivity requirements that you need for this method. So it's really a nice mass spectrometer. You don't need to buy the top of the line, most sensitive for this particular analysis. But if you are looking at some other analytes besides the haloacetic acids that require more sensitivity, the Quantiva is also an option and will work quite well with this method as well. In terms of the experimental details, coupling the IC with the TSQ Endura, I did a calibration curve ranging from 0.25 to 20 parts per billion, and again, I included all 9 of the haloacetic acids, as well as 2 additional compounds, bromate and Dalapon, which is a pesticide. So total we have 9 analytes of haloacetic acids, 2 more, bromate and Dalapon, and then we have internal standards added as well. This chart right here shows the 4 internal standards on the bottom right, Dalapon and bromate, the masses that I used, as well as the collision energies and precursor mass and product mass. You'll note here on my parameters that my temperatures, the capillary temperature and the vaporizer temperature, are both at 200 degrees C. And anybody who has used LCMS before, you might think that that is a little bit low. The reason being, just as the compound is sensitive to the temperature of the column, higher temperatures in the ion source can cause degradation of the haloacetic acids before they get to the mass detector. So we studied the optimal temperature range and found that 200 degrees C on both of those settings on our instrument was the optimum temperature in terms of sensitivity. Going higher than that, we started to thermally degrade the compounds and lost sensitivity. So just a schematic showing how everything was hooked up. If we start on the top left, we've got our IC pumps delivering water through the Eluent generator, creating hydroxide ions in this example. We go through a trap column, and then we inject our auto sampler right before our separation column, which again is the AS24. There's also the guard column on there that it's not in this picture, but that is located just before the separation column. We do our separation of our haloacetic acids. The results then, or excuse me, the flow goes through our suppressor, which is the box that you see right here. After we go through the suppressor, we removed our potassium ion from the system, and we can get a nice background for our conductivity detector to take a conductivity trace. And after that, we can go to the mass spectrometer because we've removed all the potassium ions, and that will not contaminate our system. You'll see we've got a makeup pump here on the far right. What that does is we're teeing in a small flow of organic material or organic solvent into the flow prior to the electrospray source. And the reason we do that is just to help out with the ionization. 100% water certainly works on the mass spectrometer, but if you add a little bit of organic, we get better nebulization, better droplet formation in the source, and that helps everything just ionize better and give us a little bit better results. So we used isopropyl alcohol, but you can also use acetonitrile. The nice thing about isopropyl alcohol is that it's a little bit less expensive, and acetonitrile also had some availability issues a few years ago. So using isopropyl alcohol in this example works just fine. So you can use either one. The isopropyl alcohol does give a little bit higher back pressure than acetonitrile, but it works just as well. Okay, so here's a chromatogram showing the haloacetic acid mixture at a concentration of 1 part per billion. These are all 9 of the haloacetic acids here on the trace. You'll see that each of the chromatograms has kind of a data window. So for example, in the monochloral acetic acid here, we're not scanning the entire hour for each analyte. We just tell the mass spectrometer to scan for a couple of minutes before and after the expected retention time. And that just allows us to have a little bit better, a little bit smaller data file size, so it helps with data management. There's no reason to be collecting a flat line for 45 minutes when your analyte only comes out over a span of a couple minutes. So you can see they basically elute in order of molecular weight. So the more simple, the monochloral comes out first, and we've got monobromo, then we go to dichloral, dibromo, trichloral, etc. And the last one to elute is tribromoacetic acid at about 46 minutes. This is another view of a chromatogram. In this case, what we've done is actually use a synthetic matrix. So LSSM is a laboratory synthetic matrix. The EPA requires that users will inject this synthetic matrix at the beginning of each run. And what it does is simulate basically the worst case scenario in terms of a water matrix that you would see with salts in it. And what you need to do is check the retention time because sometimes that matrix will cause a shift in your retention time. So what the EPA says is inject this sample at the beginning of the run and make sure that the mass spec windows are set appropriately so that you don't miss the peak. So that is injected at the beginning of every experiment. So if we overlay all the chromatograms from the haloacetic acid and bromate and Dalapon are included in this, you can see they kind of form 3 different groups. These are normalized to the highest peak, which is dibromoacetic acid. So it's a little bit difficult to see some of the late eluting compounds, but when you use the software to quantitate these, you can see those a lot easier than you can in this view. But what I wanted to illustrate here was outside of those 3 groups, we divert our mobile phase to waste. So basically, those red arrows that are shown on this diagram is when we're diverting to waste. And that's when we're going to have the matrix in the water samples eluting. So by shunting that to waste and not letting it go to the mass spectrometer, we can increase the robustness and uptime on the mass spectrometer. And here is the conductivity trace showing those analytes in the synthetic matrix. So when we divert those to waste, we eliminate the salts from the matrix, we eliminate the salts from entering the mass spectrometer. So we've got chlorides, sulfates, nitrates, and ions that are shown right here. And as long as they're falling within the correct divert windows, we don't have to worry about those getting into the source of our mass spectrometer. So here's just a quick calculation of our detection limits for the haloacetic acids using the method 557 on ICMS. On the first column, this is a calculated using the student's t-test of replicate injections, 7 injections of the detection limit. Most people need to get to a limit of 0.5 ppb in the laboratory. So you can see we're below that on all the compounds here. Just for comparison, I put the detection limits for 552 in the far right. And you can see that you do get the sensitivity that you need with that method. But again, that requires derivatization as well as a liquid-liquid extraction. So the advantage being with the ICMS that you can eliminate those steps. So for our first half of the webinar today, we showed the analysis of the 9 haloacetic acids as well as bromate and Dalapon using ICMS-MS. We were able to exceed the requirements for the EPA method in terms of detection limits. No derivatization steps required prior to the analysis. Really, the only thing we needed to do was to add the internal standard to the samples prior to analysis. There's low chemical noise, which is achieved using our suppressor. That helps to increase sensitivity and, more importantly, for the mass spectrometer, eliminate the ion potassium, which can cause suppression and foul up the ion source. We get really nice separations and selectivity with the haloacetic acids. We've got the temperature control, which is important for this method, holding the column at 15 degrees C. MS offers the specificity and sensitivity compared to single quadrupole because we have the MS giving us unique product ions and parent ions for these molecules. So if they coalute, we're able to separate them one from another. And the TSQ Endura triple quadrupole mass spectrometer gave us the performance we needed at a nice price point. Just a little slide to show what other applications can be run using ICMS with a triple quadrupole. A lot of laboratories are interested in doing more than one analysis on a piece of equipment, and here are some of the compounds that we're looking at and do work well on the ICMS. The popular one now being polar pesticides in drinking water as well as in food products. The big one that we're hearing a lot about is glyphosate, which is the herbicide Roundup. So in the U.S., Roundup is used on genetically modified crops as well as in the garden section. I have some in my garage. A lot of people use it to kill weeds. So that's become a herbicide of concern. It's a possible carcinogen. I think that is still being studied at this point. But there's a lot of interest in analyzing that compound, and IC is really a nice technique for the separation and retention of these compounds. Another analysis that can be done using ICMS is perchlorate in drinking water. And then, as I mentioned in one of my beginning slides, that there are going to be more haloacetic acids, some of those including iodine, that will be of interest, and those can be applied later to the ICMS as well. Okay, so now we're going to switch gears a little bit, still talking about drinking water, but I'm going to talk about a different method, EPA 543, and we're going to switch gears and use HPLC instead of IC in this experiment, but we'll still use a triple quadrupole mass spectrometer. So EPA 543, the official title is the determination of selected organic chemicals in drinking water by online solid phase extraction, liquid chromatography, tandem mass spectrometry. So this is a new method. It came out last year, and it's really the first method from the EPA that uses online solid phase extraction and pre-concentration. Previously, there would be offline pre-concentration and solid phase extraction, and then you would dry the samples down, reconstitute them, and then analyze them that way. So anybody who's done the EPA methods for LCMS is probably familiar with that. So the scientists at the EPA in Cincinnati, Dr. Jody Shoemaker, started and validated this method and released it. She chose one of the existing methods. It's actually EPA 540 that she chose, and made this the analog of, or excuse me, the online solid phase extraction analog of that method. And you can see the analytes that are included in this method. So there's 7 different pesticides that are included in this method. We're going to talk a little bit about how we do that online pre-concentration and solid phase extraction. We're going to use a system called the eQuanMax Plus system, and we're going to couple that to the Quantiva triple quadrupole mass spectrometer. And here's a picture of what that would look like in the laboratory. Again, it's a desk or a benchtop system, a little bit wider than the IC, but not too much. The extra width is due to the second pump that is required for the online solid phase extraction. We're using a trapping column, which is a water Oasis HLB, and the LC separation column is a AQ column, 100 by 2.1, 2.6 millimeter column. The method allows for up to a 2 milliliter injection directly onto that online solid phase extraction cartridge using a drinking water matrix. Even though you're allowed to use up to 2 milliliters, you don't have to. And in my example, I actually only injected 1 milliliter because I had more than enough sensitivity with that. So EQUAN Max Plus, let me give you a background of what that is. The EQUAN, the E stands for environmental, QUAN for quantitation. And we can use this for targeted quantitation, which is what I'm going to talk about in today's presentation. But I just want to let you know that it can be used for targeted or non-targeted screening applications and quantitation using one of our high-resolution accurate mass or Orbitrap-based systems. So while that's beyond the scope of this webinar today, I just want to let you know that the flexibility is there for either mass spectrometer. So what is EQUAN Max Plus? It's basically a turnkey method for analyzing environmental water samples. So drinking water, groundwater, river water. We even have some of our customers analyzing brackish water or seawater using this system. The nice thing is that it allows you to get to low detection limits, oftentimes in the low or sub-part per trillion levels. And again, it brings that online, that cleanup and sample prep online and eliminates the offline pre-concentration. The system has 2 columns. One will be your loading column or online solid phase extraction column, and then we have our traditional analytical column for the separation of our components prior to analysis with the mass spectrometer. We use 2 HPLC pumps, and our system is capable of an injection volume range from 1 milliliter up to 20 milliliters. To be honest, most customers are just getting sufficient results with 1 or 2 milliliters. A few will go to 5 milliliters, but the 20 milliliter isn't very commonly used, but it can be done. I know 20 milliliters does sound like a lot, but if you think of going from 5 milliliters to 20 milliliters, that's really only a 4x increase in injection volume and potential recovery. So it's kind of a special case to do 20 milliliters, and the most common is 1 to 2 milliliter injections. The nice thing about the EQUAN system autosampler is a CTC-based autosampler. If anybody's familiar with the CTC, it's the same autosampler. The nice advantage is that we have 2 injection ports on this system. And what that allows you to do is, if you're doing regular injections where you're not doing pre-concentration, you can inject directly to the analytical column without changing any plumbing or tubing or disconnecting pumps. So by using the 3 valves present on the autosampler, we're able to achieve that. We have 2 injection volumes and 1 switching valve. So that's really nice if you're using the system for different experiments. So EQUAN Max Plus for targeted quantitation, I'm again going to use the EQUAN Max Plus with the TSQ Quantum series instrument. Again, the TSQ Quantiva is the instrument we're going to use in this experiment, but you could use the Endura or Quantum Access Max. We can do positive and negative switching on our mass spectrometers. This analysis is only positive ionization, so we didn't have to change, but it is capable. We use TraceFinder software. That's our acquisition and data processing software that we use for our mass spectrometers, and those contain some built-in SRM parameters, as well as the built-in method for EQUAN, so that it's easy to get started with the experiment. As I mentioned earlier, you can do non-targeted screening and quantitation by using our high-resolution accurate mass instruments. Some of those you may have heard of: Orbitrap family, Exactive Plus, or Q-Exactive, or the Q-Exactive Plus. I just want to point out that the EPA method for 543 for this particular experiment uses a triple quadrupole. So this would not be applicable for this specific method to use the Orbitrap instrument at this time. So if you're doing screening experiments or something like that, that is something that you could use the EQUAN system for, coupled to the Orbitrap instruments. So as I mentioned earlier, we get rid of our offline pre-concentration and solid phase extraction step, and the big thing here is time savings. One of our collaborators, Dr. Heinz Singer in Switzerland, prepared this slide. It was how long it was taking them to analyze, prepare 1 liter samples prior to analysis on their mass spectrometer. So for 40 different samples, they would take a 1 liter sample, filter that, add internal standards, and then they would go through the solid phase extraction process. And in their laboratory to manually process 41 liter samples, it took them about 2 days to do that process. And then from there, they would load them on the mass spectrometer, and his run times were about an hour, so about 40 hours to run those 40 samples. And what they thought was, hey, is there a way we could combine this offline extraction into an online extraction and let the instrument take care of that? That would save them that 2 days of time and free up the system to run more samples and also eliminate that tedious and time-consuming offline pre-concentration step. It also allowed them to save money because they didn't have to use new solid phase extraction cartridges for each analysis. The column that's on the eQuant system is reusable, so we clean it between injections and we can reuse that. A lot of times for drinking water, I've had customers report up to over 1,000 injections of sample on that column before it needs to be changed. So what do you get when you inject a higher amount of sample or a larger volume on the column? I've got an example here showing atrazine, which is a herbicide, at the level of 10 parts per trillion. If you inject that directly, a 10 microliter injection, you're not going to see anything. There's just not enough sensitivity there. But if we inject a 1 milliliter sample here, you can see it's easy for us to detect the presence of atrazine in a groundwater sample. So that's what we're doing. We're putting more sample on that pre-concentration cartridge, and by doing that, we can see lower levels by injecting a larger volume. Okay, so back to the EPA 543 experiment. I collected my samples from various tap water sources in the San Jose area, and any of the standards, calibration standards, and QC samples were prepared in deionized water. All the samples, calibrators, blanks, and quality control samples had the 3 internal standards added prior to the analysis, and those 3 internal standards are listed here. Again, a 2 milliliter injection volume is allowed. I actually did a 1 milliliter injection volume just because I didn't need the additional 1 milliliter. It saved me a little bit of time on the injection step because a 2 milliliter injection, the syringe, we have to push the syringe of the autosampler a little bit slower due to back pressure. So it saves a little bit, 3 or 4 minutes on the injection by only doing a 1 milliliter injection. The drinking water matrix basically was a synthetic matrix similar to our previous haloacetic acid mixture. And there are preservatives added to all the samples, QCs and blanks. Those preservatives are shown here. So those need to be added at the point of collection as the scientist who's collecting the drinking water standard needs to add these at the time of collection at the concentration shown right here. And those are pretty common preservatives in EPA methods. There are some other EPA methods that show the exact same preservatives. So it's a fairly common set of preservatives that the EPA adds. For our loading pump, this is the pump that's going to take the sample from the autosampler and put it on the loading column. We had 2 mobile phases, water with 20 millimolar ammonium acetate and acetonitrile. You can see the gradient here. We load at a high aqueous, so 100% water, and then the acetonitrile step is there to wash the column. After we've eluted everything off in that column, we can give it a back flush and clean it so that it's ready for the next sample, and that's what the acetonitrile step is for. The Eluent pump, which is another HPLC pump, it follows a standard reverse phase type gradient for a C18-like column. Again, water with 20 millimolar ammonium acetate and acetonitrile, and that gradient starts out at 98% mobile phase A, and that's ramped all the way up to 100% acetonitrile through the method and then re-equilibrated for the next injection. The runtime here was just over 21 minutes for this analysis. I put up a chart here of the mass spectrometer conditions. Here we've got the masses and the product ions, precursor and product ions shown here, and the collision energies. Heated electrospray source, we had our temperatures at 300 degrees C and our sheath gas and auxiliary gas settings, which was nitrogen shown here, and sweet gas, also nitrogen, which helps keep the source clean. One of the calibration curves for one of the compounds, 3-hydroxycarbofuran. This shows the calibration range from 0.5 to 200 nanograms per liter, which is parts per trillion. So we got down to, on the low end, that's 0.5 parts per trillion, or 500 parts per quadrillion, PPQ, which is always fun to say. That's the new, or I guess it's not new, but it's one that we get to say now because the detection limits on these techniques are getting down into that range that we could say PPQ now. So that's kind of fun to have. I'm showing a calibration, or excuse me, I'm showing a chromatogram of one of the calibration standards here. There was a mixture of all of the compounds, and they were either at 6 or 15 nanograms per liter. We have an application note that details this in greater detail, and we're going to make that available here as part of the webinar. But you can find out more information on the concentrations in that application note. The internal standards are also shown here. There's 4 different internal standards, and those are used for the quantitation. So again, a total runtime was about 21 minutes. I'm only showing a window here of about 11 minutes. The time at the end was to re-equilibrate the column and get it ready for the next injection. So I've got a table here showing the detection limits that we achieved for the experiment here, and a calculated LC-MRL, which uses a calculator supplied by the US EPA. And you can see the values that we achieved there. Again, there's a chromatogram of that mid-level calibrator. So we were able to achieve the detection limits that were required by the EPA method. So just a summary on the 2 experiments that I discussed in today's webinar. We had the first section on EPA 557, which was the analysis of haloacetic acids in drinking water, direct injection of drinking water samples. We used ion chromatography coupled to triple quadrupole mass spectrometer for the quantitation of 9 different haloacetic acids, plus bromate and Dalapon. And then the second half was a summary of EPA Method 543 for the analysis of pesticides in drinking water. That was a little bit different. We used HPLC. Again, though, direct injection of drinking water samples at low part per trillion levels without any offline pre-concentration or solid phase extraction. The Equan mass system is what we used, coupled to the TSQ Quantiva triple quadrupole, and we were able to quantify 7 different pesticides in drinking water. And again, both of these are available in application note form in a PDF that information will be supplied at the end of this webinar. So with that, I would like to open up the presentation for a Q&A session. So I think that Brenda will give some instructions here on how you can enter your questions. Thank you very much.
Thank you, Jonathan, for that informative presentation. Before we get started on the questions, I do want to remind our audience how to submit your questions. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to get to as many questions as we can. Our first question, we have an audience member who asks, when using Equan, how many injections can you get before the pre-column needs to be changed?
Yeah, that's a good question. For drinking water analysis, we're typically seeing customers achieve around anywhere from 500 to 1,000 injections on the pre-column before it needs to be changed. That can vary with the amount of salts that are present in the drinking water, or total dissolved organics, things like that. We have customers that are analyzing things such as river water or lake water, and they'll get on the order of 300 to 500 injections because they're a little dirtier. And we actually had a couple customers that will run seawater or brackish water, which is quite salty. That can be done using this technique. And it's about the same number of injections, between 300 and 500 for the pre-column. In terms of the longevity of that column. When you do those types of analyses, sometimes you'll need to adjust the pre-column wash step so that you make sure to remove all of the salts from the column before doing the switch and eluting them on the analytical column. You don't want the salts obviously going to the mass spectrometer. So small adjustments may need to be made on the pre-column LC step so that you get that wash in there, similar to using solid phase extraction for the same type of sample.
Thank you. Our next question, what other types of analyses can be performed using the Equan?
Yeah, so this was just an example where we showed an EPA method that has recently come out, but we have customers using the Equan analysis for quite a variety of experiments, everything from personal care products and pharmaceuticals in drinking water, such as pharmaceutical drugs, antibiotics, even drugs of abuse that might be present or their metabolites in drinking water can be used for Equan. You can also use it for pesticide analysis. That's a big one. As we saw, these compounds are pesticides. So we have customers that are doing a large pesticide screen of several hundred pesticides using the Equan injections. We've also seen people use it for perfluorinated compounds. So things like Teflon, PFOA, PFOS are some of the common ones that are brought up. That can be also analyzed using Equan. So basically any analysis that's done with drinking water or groundwater or river water where you need a good sensitivity, and traditionally you've had to do an offline pre-concentration step. Pretty much any of those methods can be tried and run successfully using Equan with triple quadrupole. I just also wanted to mention, I mentioned briefly in the presentation, but this can be coupled to our other mass spectrometer platforms besides the triple quadrupole, which includes our Orbitrap-based instruments, that are Exactive and Q-Exactive for doing high-resolution, accurate mass experiments. So those can be used to do like an Equan screening experiment where you're looking at full scan data to look at all the compounds that might be present in a water sample and try to identify those using the high-resolution capabilities of those instruments.
Thank you, Jonathan. That's quite a bit of information. We have another question. What software is used to control the ICMS system?
Yeah, so the ICMS system, the IC, of course, came from Dionex Corporation when we bought Dionex several years ago, and they have a software called Chromeleon that some of the people on the call might be familiar with. Chromeleon is a data system that can work with a lot of different instrumentation, and the good news is it certainly works with our ICMS system. So Chromeleon, if anyone is familiar with that software, can be used for the ICMS analysis. We also have the capability of using our software. Anyone who's familiar with thermo mass spectrometers has probably heard of Excalibur. Excalibur still certainly works with this combination, ICMS, as well as our newer platform software called TraceFinder. So both of those options. So we really have three options for the ICMS: Chromeleon, TraceFinder, and Excalibur. All of them work equally as well. Sometimes it's a matter of familiarization. If a customer already has Chromeleon, they would prefer to stay with Chromeleon, so we can do that. And if they are familiar with Thermo's Excalibur or TraceFinder, we can certainly do that as well. So a little bit of flexibility there.
Thank you, Jonathan. We have no more questions, but I want to ask our presenter, Jonathan Beck, if he has any final comments for our audience.
I just wanted to thank everyone for listening to the presentation today, and thank you for coming to learn some about our techniques to make environmental analysis faster and more productive in your laboratory. Please keep an eye out for future applications on the Equan solution, where we're doing more environmental applications. Perhaps the EPA is going to promulgate some more methods for the online pre-concentration. That's always exciting to have more options for that technology. And likewise with the ICMS. Keep your eyes open for more applications next year on other pesticides that can be analyzed using ICMS. Thank you.
Thank you, Jonathan. I would also like to thank our sponsor, Thermo Fisher Scientific, for making today's educational webcast possible. This webcast will be available for on-demand viewing through May of 2016, and our audience members will receive an email from LabRoots alerting you to when that webcast is available for replay. We invite you to forward this announcement to your colleagues who may have missed today's live event. Again, thank you for joining us. Hope to see you next time. Goodbye.